Good afternoon, everybody. It gives us immense pleasure to introduce today's distinguished speaker, Professor Subrata Sen from the Shiv Nadar Institute of Eminence, India. Professor Sen is a leading figure in synthetic and medicinal chemistry, and we are truly honored to have him with us today.
Professor Sen obtained his PhD from the University of Missouri, USA, followed by postdoctoral research at Colorado State University. His rich professional journey spans both academia and industry, having served in reputed organizations such as BASF India, Pfizer, VMPS, and Sanjin before joining Shiv Nadar University in 2013. He became a full professor in 2019.
He has held visiting professorships at renowned institutions across the world, including the Julius Maximilian University, Germany, Institute Kochi, France, Middle Tennessee State University, USA, and the Applied University of Freiburg, Switzerland. With more than 114 publications and patents, Professor Sen's contributions to the field are remarkable. His achievements have been recognized globally and most notably, he is the first Indian to receive the prestigious 2025 Royal Society of Chemistry Horizon Prize, the Perkin Prize. He is also a Fellow of the Royal Society of Chemistry and recipient of the Shiv Nadar University Excellence Award and the Swiss National Science Foundation Research Fellowship.
Request our
quite a crowd, and I hope there are questions at the end of the lecture. It's okay. We welcome you, sir, to this campus, which is no longer very new. It's quite 7 years old, but nonetheless, we are still green in terms of our achievement. We have to sort of go a long way, and you are confronted with a bunch of students who are really eager to hear you. So I shouldn't stand in between. I would very much welcome you to deliver your lecture. Sure. Thank you.
Thank you, sir.
Come here.
Today, Professor Sen will be delivering a distinguished lecture titled From Light to Electrons to Mechanical Force, Modern Green Pathways to Heterocycles. Now, before we begin with the lecture, may I request our Founder Vice Chancellor, sir, our Dean, and our current head of the department to felicitate Professor Subrata Sen as a token of respect and appreciation.
Papya, should I start?
Yeah, sure.
Great. Fantastic. Good afternoon, everybody. It's a pleasure to be here. Yeah, usually the felicitation happens at the end of the talk. So when it happened at the beginning, I was like, okay, now I can grab my gifts and then walk out. So, but that's not the point. So I really enjoy interacting with students and talking to them about science. So I thank Sister Nivedita University and and also Papia and all of you over here for this warm welcome. And this is really nice. So today I'll be talking about a very interesting aspect of our research. As during my introduction you came to know that I used to work for industry for a while. So when I moved to Shiv Nadar University around 2013, my initial work was primarily based on medicinal chemistry, conventional organic synthesis using metal catalysts, iodine as reagents. And then over the years, we started to work, but we were becoming a lot more conscious about the environment. And that is when somewhere around 2018, 2019, we thought about trying to make a paradigm shift of our research focus from traditional thermal organic chemistry to something which are much more sustainable. And that was the time when we started to think about using less energy intensive strategies to perform organic reactions. And using photochemistry, electrochemistry or mechanochemistry, and at the same time try to avoid using organic solvents and definitely metal catalysts. So our reactions, what I will show you today, we try to avoid them, but as you all know, it's very difficult. But at the same time, the way we look at it is that ultimately when we try to prepare a product, especially heterocycles, how atom economical it is and how novel the strategies are. So we don't have solutions to all the problems, but what we do is as one of the 1/1,000,000th of a scientist working in these kind of projects, if we each start to think about contributing to the environment in their own ways, cumulatively this will become an effort which will help us for environment sustainability, retaining our renewable resources and etc. So when we moved away from the thermal reactions to photochemical, electrochemical or mechanochemical reactions, we had two options to work for. One option is to perform reactions in presence of photocatalysts or electrocatalysts, and at the same time, what happened is we wanted to move away from metallic photocatalysts. So one option was to use organophotoCatalysts, or the other option was to try and utilize a substrate which is very versatile and robust, and that will help us to generate different kinds of heterocycles. As I said, we cannot replace thermal reactions. It's not always possible, and it has been there for more than 100 years. So if we have to replace with something, at least we can try and emulate some of its, remove some of those thermal reactions and try to use them. So the way I have divided my talk is that initial part, I will give you a brief, background of what our lab do for last 5-6 years based on these photochemical, electrochemical, and mechanochemical reactions. And then lately, we have started doing a very interesting chemistry using mechanochemistry. And the primary aspect of my talk will rely on that particular chemistry. So when we were talking about the substrates, a suitable substrate that is going to help our problem and which can be very versatile, we thought about these kind of diazocarbonyl compounds. So these diazocarbonyl compounds, we all know that if you irradiate diazocarbonyls, it will get excited to become a singlet, and then through intersystem crossing, it will become triplet. And consequently, you're in the triplet state or in your singlet state, it can lose nitrogen in order to give either a singlet carbene. It can give you either a singlet carbene, which can be used as an amphiphilic molecule, or it could give you a triplet carbene, which can be used as a radical. So we chose about working with this carbene moiety, and majority of our work when it involved photochemistry, or rather electrophotochemistry, it involved the singlet carbene. Because the advantage of this molecule is that and in the vicinity of a nucleophile, it will act as an electrophile. The nucleophile attacks it, and then itself it will go ahead and become a nucleophile and can attack an electrophile. So this ambivalent nature of carbenes enabled us to do a lot of different reactions, develop a lot of heterocycles, and that's was really interesting. So when we look into in retrospect, the history of these carbene molecules, as you can see, there are quite a different kinds of carbenes which are available, electron withdrawing carbenes, and then we call these diazomalonate carbenes, then you have carbenes with electron donating group and electron withdrawing group, and then our favorite aryl diazocarbenes, and then diaryl carbenes and aryl carbonyl compounds. If you really look into the history of publications, the first time such kind of reactions which was discovered with these carbenes, though not with light but with metal like rhodium, was 1988. Then as the time progresses, somewhere around 2014, the blue LED became one of the very crucial aspects from the Japanese scientists, and that's how they got the Nobel Prize. And you will notice that from this area onwards, the reactions of blue LED induced carbenes have started to really surge, and that is where when we also picked up the momentum somewhere in 2018, 2019, and then now slowly it is the way it's happening is that the euphoria is slowly dying, because that's what happens for a typical scientific aspect or a new scientific discovery. It stays there for a decade, and you get make the maximum out of it. Not all the reactions are Suzuki coupling or palladium catalyzed CC bond forming reactions, or for that matter, diversity-oriented synthesis. In general, you need to make the best out of a particular research area for 10 years, then you slowly move ahead, try to find a new one, which would be able to give you a newer set of solutions for a different set of problems. So let me take you through what we did a little bit about on photochemistry. Our main research focus for last few years were in photochemistry. We have close to 30-35 publications in this blue LED induced reactions. Obviously, because of paucity of time, I will not be able to take you through all them. So let me quickly go take you through these photochemical reactions. This particular reaction is very interesting. So as you can see, this is your aryl diazocarbenes. And these aryl diazocarbenes, what we did in presence of 1,4-dioxane, oxygen nucleophilic, it is going to form oxoniumylide. Now the beauty of this intermediate is that it makes this carbon very electrophilic. So if you bring in any nucleophile, it is going to open up this CO bond, and as a result of which you are going to get these dioxo molecules. We have also tried this reaction in presence of crown ethers, and the reaction also works, giving you polyoxo molecules. The idea was that if we have these nucleophiles as drug molecules, I mean the pharmaceutical drugs, then what happens? We could use them to go ahead and make this kind of tethered molecule. Now, these polyoxo molecules or dioxo molecules are very useful to make drugs druggable. It is not always the efficacy of a drug that is important, but also how well you can allow and administer the drug that it goes to your particular organ, target organ. And in those cases, to make those drug molecules robust, you have these polyoxo molecules you can prepare. Another interesting aspect what we have done over here is, if you notice this reaction where you do not have any nucleophile, what happens? There is like a ring expansion. This negative charge attacks over here and this CO bond breaks. So from this 1,4-dioxane, you got 1,4-dioxypene. This concept is called skeletal editing. That means you have taken a dioxane and you have just very specifically, precisely, you have inserted a C substitution in between the CO bond, as a result of which you have converted the structure of 1,4-dioxane into 1,4-dioxypene. Another interesting aspect is, just as I've shown you this 1,4-dioxane, with oxonium-ylide, we have this your pyridinium-ylide. And this pyridinium-ylide happens in the same way. Under blue LED, the nitrogen, it liberates, you get a carbene, nitrogen being nucleophilic, the pyridine, it forms this pyridinium-ylide, which is a very nice 1,3 dipole. This 1,3 dipole with an appropriate dipolarophile can undergo 3+2 cycloaddition. The rest of this transformation was entirely serendipitous. We have nothing to do with it. We thought that we are going to get this molecule. Interestingly, the arginase for the pyridine to rearomatize, and this particular CC bond is quite susceptible to oxidation. So what happens is that this gets oxidized first, the pyridine rearomatizes, this bond returns over here, and the oxidized double bond attacks, and we end up getting these kind of molecules which are called itaconimides, which have very interesting natural products for antibacterial and antiviral. In another aspect, using the same photochemistry and diazocarbenes, what we did was we prepared these small molecule analogs of a natural product called pyroformadine. Pyroformadine is an anti-cancer compound which works as it binds to polyadenosine ribose polymerase, PARP inhibitor, which essentially helps in the rectification of the double-strand break of DNA. So cancer cell hijacks that methodology. So as a result of which, if we can make a drug molecule that binds with PARP, then the PARP won't be able to do its original function, then we can get an inhibitor against cancer. So when we made these molecules, as you can see over here, we have tested them against few cancer cell lines. The activity, the IC50 is in the range of 600 nanomolar, which is nothing great but not bad either. We have also shown that it binds to the PARP and it inhibits to about 1.5 micromolar. In another reaction, what we did was we wanted to see how our diazocarbenes and 1,4-quinones are compatible with the reactivity. So when we took different kinds of these diazo esters and reacted with different kinds of 1,4-quinones like benzoquinones, methylbenzoquinones, naphthaquinones, anthraquinones, we could see that there is a relationship between the electronic nature of these diazocarbonyls and the electronic nature of these quinones, and there are different site selective operations. Like for a particular case, it gives you these kind of spiroepoxides. In another case, it gives you these cyclopropane molecules, and in some cases, it gives you a direct substitution. A few years back, I worked with Debobroto Maiti in IIT Bombay, where we have shown a very interesting transformation that if you develop these carbenes in presence of nitriles and blue LED, then the nitrile inserts over here to give you a 3+2 cycloaddition, and this particular molecule undergoes intramolecular 3+2 cycloaddition in order to give you these 1,3 oxazoles. We developed about 80 different analogs of oxazoles. Interestingly, when we perform the exact same reaction in presence of a nucleophile, which is basically an isocyanate, instead of this intramolecular reaction which we have demonstrated over here, we could get a geminal diamination, giving rise to alpha-alpha substituted amino esters. So, like what I am trying to like convey over here is that obviously with blue LED and with diazocarbonyl as substrates, we can access different kinds of your heterocycles. And moving on to the next, our phase of reactions, again, I will just show you a few of our. So from photochemistry, we also started doing electrophotochemistry. For example, in electrophotochemistry, we have demonstrated that in presence of blue LED and light, only blue LED provides you a carbene, but in presence of blue LED and electricity, you are going to get a carbene anion radical. We have proven that your diazo compounds, they undergo reduction in presence of cathode, followed by elimination of nitrogen in presence of blue LED. Now you can take this intermediate, and depending on the sequential addition of these maleimide, you can get two different kinds of products. If you have the maleimide from the very beginning of your reaction, then what happens? This gives you a sequential reaction to give you a 5,5 product, with this 5,6 product as a minor. So what is this 5,6 minor product? So obviously, in absence of this maleimide, what happens is that this radical undergoes insertion with this nitrile to give you 1,3 oxazoles. And then they undergo a 4+2 cycloaddition in similarly like a Diels-Alder, giving you a 5,6 motif, which when you in presence of acid gives you a vitamin B6 analog. We utilize this concept of radical anion with different kinds of radical cations. So we bring in different kinds of heterocycles, and we could demonstrate a direct NHC oxygen S insertion reaction. So this is an example of a convergent pair electrolysis. So your diazo is undergoing a radical anion, the corresponding heterocycle undergoing like a radical cation oxidizing at the anode. So the reaction between the radical anion and radical cation are much more efficient. So similar reactions which were done in presence of a base or metal catalysts, or in presence of just light, when we do the reaction in presence of both light and electricity, we could see that the reaction time is reduced a lot, and at the same time the yields are pretty high. Last year we did something very interesting. In electrochemistry, the main thing, the principle is very simple. You charge DC current. Your like one of your reagents, depending on their potential, will undergo reduction at the cathode, oxidation at the anode, and then the correspondingly anion and the cation are going to work. Now, during these electrochemical reactions, there is a formation of electric double layer, which means in front of the anode there will be a counter ion which will form, and again at the same in the front of the cathode, your another counter ion is going to form. As a result of which, under DC current, as you proceed, after some times, because your reagents present in your electrolyte, but the reaction happens on the electrodes. So your reagents find it very difficult to reach your electrodes, because there are these electric double layer. So as the reaction moves on, you tend to get your yield reduces, the resistance increases, the reaction heats up, so it becomes very inefficient. Phil Baran from Scripps Research, he conceptualized a new way of performing this reaction, which he called RAP, or RAP as we call it. It is rapid alternating polarity, which means that over a period, your anode and cathode are going to change their nature. So the anode is going to become a cathode and the cathode is going to become an anode. When they change, their corresponding EDL will dissipate and the reaction will become efficient. Unfortunately, when these periodic changes happen, there is always a resting period in your reaction. Subsequently, your reaction time increases. What we did was, we used a couple of electrodes. We used 2 pairs of electrodes instead of a rapid alternating polarity, where they are connected through a microcontroller. So when the first pair of electrodes are working, and say after 50 seconds or 100 seconds, the microcontroller changes it to the second pair of electrodes. Subsequently, what happens? You are always getting after every 100 seconds or 150 seconds, you're continuously a fresh electrode. So that resting period, what Phil Baran proposed, we eliminated from our reaction. As you can see over here, our current density remains constant all over your entire reaction. So we have provided a procedure which improves Baran's concept of RAP. And this was one of the main reasons why we received the corresponding RSC award for the Perkin Award. Though it is severely criticized, even it is being criticized right now. Whenever I submit a paper with our AEE, I get the reviewer comment saying that how different it is from RAP. So we have to do a thorough experiments from DC to RAP to AEE, showing that the current density, the potential density, the time, the resistance, everything is improved in AEE over your RAP. The same thing happened with our recent publication, where we have taken a maleimide in presence of different alcohols, and then in presence of a diazo, we could see that we can very nicely convert this into a substituted diastereomeric succinamides. And this we just submitted to JAX-AU for a revision, and there the main point was, why are you calling it AEE, why not RAP? So that's the white supremacy is ruling, so but we have to continue our fight. So moving on to our another set of reactions, what we do is called using mechanochemistry. This is very interesting in a sense. We are removing the solvents. It's exactly the concept is like using a mortar and pestle. Remember, we try to do neat reactions using mortar and pestle and then trying to do the reactions instead of doing it in organic solvents. So these ball milling, basically mechanochemical ball milling is you have these small chambers, and these small chambers are going to contain metallic balls or zirconium balls or polypropylene balls, and these chambers they vibrate at a certain frequency. So the balls, they strike against each other, giving rise to an energy, and that transfers into your reagents, and as a result of which they are going to react. So we have done few very interesting chemistry with that. Though we are still at a very nascent stage in mechanochemistry, like iminoiodinanes, we reacted with different kinds of amino alcohols to give you these aminosulfones. We prepared these kind of with your iodonium ylides. It undergoes a 3+2 cycloaddition in presence of copper to give you these fluorescent probes. Very recently, we used this kind of chemistry where we took these alkylidine indoles, and in presence of mechanochemical force, we reacted with this diazochemistry with aryl diazonium borates, which forms this kind of nitrile ylides, and they undergo 3+2 cycloaddition to give you these pyro compounds. This is another a machine which we have started to work with. There is a Swiss company called WAB, Willy Backhofen. They are primarily into bead milling. Instead of ball milling, the thing is that they are using the very tiny beads, and these are typically used in the ink industry or formulation. So this company, they approached us because they want to go ahead and start using this machine for mechanochemical organic synthesis. They want us to go ahead and evaluate and then tell them what are the things they need to change to make this machine compatible with organic synthesis. That's what we are working on. So this was what was all going on in my lab. So now I will come to one very interesting project which we have completed recently, and that is like harnessing pyridinium ylides for ionic cascades, a scalable mechanochemical route to azaindazoles and related heterocycles. Let me introduce the main players of this project. This is Shubhankar. He is my PhD student. He's the final year PhD student. He is the lead synthetic chemist over here. This is Yashika, who is the second year PhD student helping Shubhankar for the same. Rafiq is was a postdoc, and he did some work over here. This person is a third year B.Pharm student from BITS Pilani, Hyderabad, and he did a lot of work when it comes to your, the optimization of the reaction. And Shomiran is also from BITS Pilani. This is a more or less, I would say, a transcontinental project, because my Swiss collaborator Ludovic is also there. and also Tanmoy Chatterjee, who is an associate professor from BITS Pilani, Hyderabad. So what we wanted to do over here, so before going there, let me give you a brief idea, and this is mainly for the students, is that CH functionalization of pyridines and heteroarenes. So the way we can functionalize the naphthalene or benzene or aromatic rings, we cannot do that for these pyridines and heteroarenes. Why? Because they are electron rich. So a simple Friedel-Crafts alkylation or acylation that happens on benzene ring, we cannot do it on the pyridine. That's like a JEE question in class 12. And why is that? Because the aluminium goes ahead and coordinates with the nitrogen, giving rise to a pyridinium halide. Similarly, in order to functionalize pyridine, you have to install different functionalities onto the pyridine, then do the reaction. So people have been working on these direct CH functionalization, where by just activating the nitrogen, you can do orthofunctionalization or parafunctionalization. Typically, these are much more easier compared to your metafunctionalization, and that is where there is a professor in University of Aachen or like Armido Studer. Studer demonstrated a very elegant way of functionalizing meta positions of pyridine, where he made these oxazine type intermediates, then did a lot of these regioselective ionic or radical CH functionalization, then simple hydrolysis gives us the pyridine. You can also do the same reaction using metal catalysts. So let me take you through what are the three ways typically where you can activate or functionalize the pyridine. What happens in a direct CH functionalization? This was a pioneer paper by Hartwig in Science in 2013, where he used silver fluoride, which undergoes a reaction with the pyridine to give you pyridinium halide. The fluoride attacks over here to give you dihydropyridine. Then under your radical reactions, the pyridine rearomatizes back to give you a library of orthofluoro substituted pyridines. Another way is functionalization via dual activator and reactive partner. It means the moiety that acts as an activator of the pyridine is also the partner which gets attached to the pyridine. So as you can see over here, you take this pyridinium halide in presence of light, you go ahead form this immunoradical and phenolic radical. Then through a 1,6 hydrogen atom transfer, this hydrogen moves over here. It undergoes cyclization, followed by an oxidation and hydrolysis, base hydrolysis to give you these kind of substituted pyridines. And then when you have a functionalization via sacrificial activator, which means your triflic anhydride or the triplet is a sacrificial activator, it activates the pyridine. The triphenyl phosphine then attacks over here because the para position of the pyridine is most active, as a result of which you get this dihydropyridine, and then the pyridine rearomatizes to eliminate the triplet. And because this is a phosphorus halide, as you can remember in Wittig type reaction, if you introduce a nucleophile, you will get different substitutions of this. So these were the premises of our, when we first started to see how we can go ahead, convert a pyridine directly to azaindazole. So these azaindazoles moiety, as you can see, they are quite there are a lot of bioactive molecules. So when we looked into the literature, as you can see, just as I spoke about a few minutes back, in order to make the azaindazole, you have to have these pre-functionalized pyridine, as a result of which you need to have multiple steps, and therefore it makes the reaction not very efficient over the, these existing reported procedure. So what we thought about was really simple. Go ahead, start with pyridine, activate the pyridine with these iodonium halides, and then this is the second USP of our project, is where you use aryl diazonium tetrafluoroborate to facilitate a cycloaddition reactions. Aryl diazonium tetrafluoroborates, we all know, is a very crucial reagent for Zandmeyer chemistry. You can make aryl diazonium tetrafluoroborate with aniline, then you can bring in any kind of nucleophiles, or in presence of a radical initiator, you can do a radical mediated chemistry, and then you can get your desired substituted benzene. But there are a lot of reactions where aryl diazonium tetrafluoroborate can act as a cycloaddition partner. There is a huge review in Chinese Journal of Chemistry where aryl diazonium salts have been used as these cycloaddition reactions, and you can get a lot of different chemistry, and that's what we wanted to leverage in this particular project. As you can see over here, not only did we use pyridines, we used quinolines, isoquinolines, quinoxalines, and then converted them. We first converted them to the iodonium halides, activated the nitrogen, and then in presence of mechanochemistry with your aryl diazonium tetrafluoroborates, we get your desired different kinds of azaindazoles. I will quickly go through it because I know I don't have much time, right, Papia? We have some time, okay. So what we did was we did a quick optimization study with different kinds of base, and obviously we found dichloroethane was one of the better solvents, but however, as you can look at the yields of the reaction, these are very poor. So next what we did was, as I was telling you, we did a neat reaction, and then we found that we don't need solvent to do the reaction as the yields were comparable even without the solvents. And that is when we converted that transformed that reaction into mechanochemistry. And as you can see over here, this is the Retz ball mill, what we have in our lab. And these are the chambers which undergo vibration, and you get different kinds of stainless steel jar with stainless steel balls, zirconium ytterbium oxide jar with ytterbium oxide balls. And then you tend to use 2-3 balls, not more than that, maximum 10 millimeter size, and they are going to strike against each other in order to give you the compounds. Another interesting part, or rather one disadvantage of this mechanochemistry is that in presence of your homogeneous solution, your reagents are very well reacted. In mechanochemistry, because there are no solvents, there is always a chance that your reagents is going to stick to the surface of your reaction chamber. So the mixing is not going to happen well. So that's why what we mix during our reaction are called grinding auxiliaries, which will smoothen the surface of the reaction, like sodium chloride, like silicate, or your silica. And as you can see over here, in presence of sodium chloride, as a grinding auxiliary, we could increase the yield to 79%. We also went back, tried the other bases which we used in solution under mechanochemical conditions. However, we found that Dabco works much better than any of the other bases. So we went ahead, we then generated the library of compounds. As you can see, we reacted the pyridine with different aryl diazonium salts, including 2 drug molecules called benzocaine and butambane. We used differently substituted pyridines like meta-iodo, para-CF3, 4,4-bipyridyl, paramethyl, paramethoxy, parabromo, and even deuterated pyridines we used to do the reaction. We also use drug molecules, natural products like nicotinamide, nicotine, and isoniazid, which works really well. We did the reaction with quinoline, with quinoxaline, and with isoquinoline. So obviously the most important part that stays is to understand what is going on in the reaction. We can do a reaction, but we have to know the control, so how this particular transformation happens. So we did quite a few control experiments. I'll go a little faster over here. So when we reacted this without a base, we could see the formation of this diazine. When we did the reaction in presence of this, under the standard optimization conditions, what we found was that, and prematurely stopped the reaction, we could also found these kind of byproducts which are formed in the reaction. And also a careful analysis of the reaction, we found we got a monoester derivative. Definitely we did a kinetic isotope effect. The students must all know about KIE. That is, we did a double deuterated pyridine and did the reaction, measured the rate of the reaction, and what we found that the unsubstituted pyridine is at least 3 times faster than your double deuterated pyridine, which makes us understand that either this CH bond or this CH bond is the one which is playing as in the rate determining step. This is the reaction mechanism. So it starts off with this halide. In presence of aryl diazonium tetrafluoroborate, it makes this diazine. This diazine undergoes a cycloaddition, followed by the re-aromatization of the pyridine in order to give this intermediate B. The intermediate B can be assumed that it is formed because we have isolated these kind of molecules which must have happened from the hydrolysis of this particular intermediate. Then it undergoes an electrocyclization followed by oxidative decarboxylation in order to give you the desired compound. As an application, we went ahead and we performed the reaction in presence of, scale up. When we did the reaction in small scale, it was around 0.25 millimoles. We bumped up the scale. We used this kind of dyno-mill, which is like a similar kind of a bead miller, in order to give your desired product in equally comparable quantity. We did a lot of downstream operations, because what happens is that it's always expected that when you formed a product, you need to demonstrate that how useful those products can be. Can they transform into some other molecules? So as you can see, when we use this picoline, what we obtained in our reaction was this analog of your corresponding azaindazole. At the same time, when you take this kind of bromo-substituted azaindazole, you can do a palladium catalyzed coupling in order to make this hydrazine. You can go ahead and you do this kind of activation by this nitrogen in presence of a copper or in presence of a rhodium in order to give this acetate substituted or sulfide substituted azaindazoles. Similarly, you can also do a Suzuki coupling reaction with the corresponding azaindazole. So it demonstrated that your end products can also be functionalized into different kinds of reactions. Finally, what we looked into the literature when we found is that these azaindazoles can act as antibiotics, because these are known to be showing their antibacterial properties. And this is a publication in Science which came out by Hergenrother, that you have this pyrazole and this pyridine, and you can prepare a gram-negative specific antibiotic targeting the lipoprotein. Though this has no direct structural resemblance to azaindazole, but it contains all the essential moieties which are present in the azaindazole. Keeping that in mind, what we did was we went ahead and screened our set of libraries against these multi-drug resistant bacterial strain, which are basically escape pathogens, like Klebsiella pneumoniae, Actinobacter baumannii, Pseudomonas aeruginosa, and Escherichia coli. In a broth dilution method, the entire project, the reaction was done in the presence of Professor D. Sriram from BITS Pilani, Hyderabad. And as you can see over here from this activity chart, is that in presence of antibiotics like erythromycin and ceftazimine, our activity of few of our molecules, it is about 12.5 microgram per milliliter. The point is that 12.5 microgram per milliliter may not be a fantastic activity, but the point is these are against multi-drug resistant bacterial strain, escape pathogens, where the general antibiotics have failed to show any decent effect. So if we look into this entire project, what we have demonstrated is a solvent-free mechanochemical protocol for dearomative CH functionalization of pyridines and related heterocycles. The entire mechanism is elide formation, aromatic nucleophilic substitution, electrocyclization, and rearomatization. It's a metal-free, mild, and sustainable with a broad substrate scope and high regioselectivity. It enables late-stage drug modification and divergent derivatization. We have shown the mechanistic proof using the diazine intermediates and kinetic isotope effect. Dyno-mill scale-up confirms industrial and sustainable applicability. Downstream operations to modify the azaindazoles, and preliminary antibacterial screening against escape pathogens. So last but not the least, I would like to acknowledge the set of students. This is my research group. So all of them are PhD student. Suchishmita is now an NPDF postdoc. This is an undergraduate student, Srikant, a final year. And then Srikant, this Tejas has already got a postdoc in Switzerland. And these others are my PhD students. I have an excellent set of collaborators. Ludovic from Applied University of Fribourg, Devobroto from IIT Bombay, Ralph from INSERM Paris, and Tanmay Chatterjee with Animesh and Parthopratim from my institute. I'm happy that Shiv Nadar Institution of Eminence have really pampered us with funds when it comes to infrastructure and manpower. They also provide faculty grants. Then I'm thankful to Zurich University of Applied Sciences and ANRF for funding. And this is the Horizon Award which I got, and this was the team which got the award. And last but not the least, in January we are organizing your conference cum workshop. So the first edition happened in 2024. The second edition is happening in 2026, which we are calling Modern Aspects of Green and Sustainable Chemistry. The workshop will contain all the green strategies used in the industry. And we have the person from BASF, Metla Toledo, IIT BHU, and from Novartis who are going to be the instructors. And then followed by a 2.5 days of lecture session where people like Eric Carrera, who is the editor-in-chief of JAX, Rahul Banerjee, another associate editor of JAX, Nakamura, then D.S. Reddy, who is the director of CSIR IICT Hyderabad, Shantanu, Partho. They will all be there and it will be a fantastic opportunity for the students to go ahead and interact with them. So with that, I will stop. I know I have just overseen the minute by few, and I'm happy to answer any questions.
Thank you so much, sir. So, anyone up for any questions? Yes.
Sir, actually, I wanted to ask you about one of the slides and all the data. Can you please rewind?
Which one?
The one behind, like just before this. Yes, sir.
Yeah.
So, what is this data? Like, could you please explain this?
Okay. So what happens is it's a MIC, inhibition of microgram per milliliter. So basically what happens, you go ahead and using broth microdilution, you want to measure the amount, the concentration of your drug against the measurement, the size of your bacterial colony that has formed. So when we look into it, we could see that this particular data indicates that lesser the value of this, the more active is your molecule. It is, as you can see, the microgram per milliliter. So the kind of effect in the inhibitory effect which has been imposed by this compound 4E is like 12.5 microgram per milliliter is the minimum inhibitory concentration, and the same concentration, like it takes about, that same inhibition needs to be imposed about 100 microgram per microliter by this particular erythromycin. So this tells you how active your compounds are.
So, I assume that these are the columns for different bacteria?
These are the columns for different bacteria.
Okay. Okay, sir. Thank you, sir.
Anyone else?
Yes, please.
Sir, can we incorporate any kind of biocatalyst in the process, what are the challenges we can face for that?
Which step you want to incorporate biocatalysts?
Like while the pyridine synthesis, like heterocycle synthesis,
Yes.
during the following the green pathway,
Okay.
we can avoid the metal catalyst and we can incorporate any kind of.
Yes. So basically, what happens? You can let me just show you one reported pathway. Yeah. So this particular reaction, okay. So suppose they are using copper as a catalyst. This indicates it's a catalyst because that's a catalytic cycle. Now, if you want to replace this particular copper with a biocatalyst, the essential problem with the biocatalyst is because it's a biological origin, you have to impose lot of different constraints in your reaction medium. So as a result of which, there are also examples where these kind of transformations has happened in presence of biocatalysts. But when you want to take it for a scale up,
Like yield.
even in a smaller scale, biocatalyst gives you good yield. It is very much sustainable. And the main problem with the biocatalyst which people tend to face is during the scale up reactions. So when whenever you are trying to develop a particular chemistry, it is assumed that it will not stay within your lab premises. It will go beyond to your a kilo lab, then to your. So when it comes to biocatalyst and when it comes to scale up in like 10 kilos, 100 kilos, and that is where you tend to face the problem. You need to impose lot of restrictions and sometimes the cost effectiveness. That's the only thing. Otherwise, there is no problem with biocatalyst. It's one of the most green catalysts that happens.
Regarding the blue LED, actually, what is the significance of blue LED? But definitely it is supplying energy, the particular energy. But why not any other light?
Absolutely. So, see, the point is, that's why I said that selecting your substrate is very important. What I did not discuss, because if I had to discuss that, it would have taken a lot of time. You can do different reactions with different LEDs. You can also do the reaction with ultraviolet light. The problem with ultraviolet light is it's too strong. It will give you a lot of byproducts, and there will be a lot of side reactions, and you cannot control the reactions. So people started to see if you can go ahead and react with under blue LED or red LED or your green LED. And the main compatibility is the absorbance of your substrate with the light. Exactly. So the blue LED is within the range of 450 to 475 nanometer. And these aryl diazotesters, as you can see, absorbs in the range of 430 to 460. So it really nearly overlaps really well. So what I have shown you, as I said, I have shown you only 5 projects. In all other projects, I have used violet LED, blue LED. The only thing is that your substrate needs to be compatible. Because again, the principle is very simple. That energy through your solvent needs to be transferred to your substrate. Then only substrate will activate and will give you a product. Unlike thermal reactions where it is quite intense, these are much more mild. So your control over your reactions are much more compared to thermal.
And that thing actually I missed what you told about this changing polarity.
Sure.
And just.
Yep, that is something which I've been explaining to a lot of people, not only you, especially the reviewers, because they still do not want to believe that somebody from India can come up with something and challenge their the Western counterpart. So what happens is, as I said, in rapid alternating polarity, your anode becomes cathode, cathode becomes anode. While doing this, there is always a resting phase. And because you need to wait for that EDA to dissipate. During that time, nothing happens. So what we did was, we took two pairs of electrodes. Pair 1 cathode anode, pair 2 cathode anode. We start the reaction with pair 1 cathode anode. Let the reaction go by, and we have programmed it with a microcontroller. What we have done some R&D with specific reactions. Because what happens when we change this, we do not do it arbitrarily. We follow the reaction and see that at what time the reaction starts to go bad. So during about few seconds earlier, we program the microcontroller so that the cathode anode changes to the newer set. So as a result of which, when it goes to the new set of cathode anode, there is no EDL, so the reaction goes smoothly.
The reaction starts anew.
Exactly. So and this switches back again to the original one. So one of the reviewers asked a question, so you are talking about 2 sets, why not 3? Why not 4? I said, you do not require 3 or 4 sets.
Exactly.
Only 2 sets is important, because it is every time you need to get a new set.
You are just alternating the sets.
Instead of the LEDs, if one were to use pulsed laser, would that have sort of given a better yield? Because the transformation of the substrate with a laser would be perhaps greater, because the photon impact would be more.
Absolutely. In fact, there are certain reactions which are also done with pulse lasers. But the problem with pulse lasers are, since their photon impacts are quite high, sometimes it tends to degrade your substrate. You don't have much control.
It will depend on the nature of the substrate.
Absolutely.
I mean,
you can use graphite. Graphite for that matter is quite strong. So you can use, there are some reactions on pulse laser also. You can do that. Right? The beauty of this blue LED is that we have shown reactions being done at 5 watt. And depending on the substrate tolerance.
Low energy.
Absolutely. We can go to 34 watt. The overall, the energy intensity is also less. And we can control the controls.
Whatever you say, is it for different reaction? We have to check for different timings for changing this?
See, for electrochemistry, you have to check the potential of your reactants, because only you know using CV that if what is the reduction potential and oxidation potential of your reactants. Only when they are compatible, then they are electrochemically compatible. And what additionally in AEs, we tend to see that to what extent the reaction's efficiency, we do it by current density. The moment, so there is a machine from ICA, which is a Swedish company, where you can measure the current density over the reaction. So there what we monitor is that to what extent the current density stays constant, and the moment it starts to fluctuate, we know that the EDL has started to develop. So accordingly, when we apply your AEE, we change the microcontroller time. Say for 25 seconds we have watched that it stays constant, then it goes down. So up to 20 seconds we keep the microcontroller, and then after 20 seconds your alternate electrodes, they tend to change. So it will definitely vary with reactions. Not all reactions are equally, the speed.
Anyone else? Thank you, sir, for explaining so beautifully. So we have our Pro Vice Chancellor, sir, Dhruvajyoti Chattopadhyay. I would like to say or call sir to say a few words.
Let me first congratulate on behalf of all of us for your fantastic, you and your team's recognition as it's okay, it's a Parkin Prize. Let me first congratulate you on behalf of our university, our students, our faculty members for doing this fantastic work, and your team for receiving this Perkin Prize. And thank you for coming over here and delivering a very interesting lecture, which actually exposed our students to a lot of new different things which are coming up in chemistry right now. Specifically what I could find it out, though you talk about the photoelectric chemistry, which is already there, and it's now people are looking at it from a completely different angle. But with respect to the mechanochemistry, what you have talked, you can see the industries right now are very much interested, because here the question of green chemistry and its applicability with respect to how that means sustainability, when you are talking about it, it's going to help quite a bit. Now, in that particular case, if I could find out that this particular LAG, that's liquid assisted grinding, and the extrusion technology, where you can see a combination of this mechanochemistry and the one you are talking about, the milling of the things with this. In this particular aspect, what I think there is something very novel your team actually done with respect to its application wise. So there, yes, you want to say something? Yeah. So in that particular area, what we could find that we are looking completely from a different angle. that the convergence of, as you were mentioning about that particular drug molecule, which is a POP inhibitor, and how it's actually becoming very important in that. In all these cases, right now, the synthetic chemistry itself has got a huge amount of this. All these concepts are going to be utilized in this synthetic chemistry, and the reason I'm feeling very excited about, just day before yesterday in China, in one of the meeting, I met one of the faculty member from Berkeley, who is actually delivering the lecture on this enzyme catalyzed reaction, enzymes in a new form. We are not talking about this bioenzymes or the metal catalyzed, where the metals are being replaced by these particular pyridine molecules, where this particular synthetic chemistry is becoming very important, and they are actually doing a huge amount of work in this particular area. In fact, Devabruta Maiti, he has got some sort of work with Devabruta Maiti also, he's mentioning at that time. So just day before yesterday, I heard from him about it, and today I could get the opportunity to meet with you. That's really an opportunity for me, and I really want to thank you for coming over. Thank you. Let's give a big hand to Professor Sen.
Their enthusiastic participation and presence. Thank you. I take this opportunity to express my deepest appreciation to our eminent speaker, Professor Shubhobrata Sen, for his inspiring and insightful lecture. This session has been truly enriching for all of us. On a personal note, it gives me immense pride and joy to welcome Professor Sen, whom I have known for a long time. We share an academic bond as well, having both completed our PhD from University of Missouri, Columbia, USA. I remain ever grateful to him for his guidance and support that helped me begin my own academic journey here. Thank you all once again for being a part of this wonderful event. Thank you so much. Okay. So, may we gather for a group photograph, please? Sir, please. Professor, can please come here. We can just.